Okay, good morning. Let's start because we have a very dense lecture, so let's start on time. Before starting addressing the topics of today, I would like just to mention that the assignment is on Portale Didattica. I think that all of you already have a chance of looking into the assignment. As the number of groups that I received, they are quite different. There are groups spanning from 1 people to 4 people. I posted a project that is with growing complexity with the number of team members. As you can see, there is a common functionality that shall be developed by all of you, no matter how big the group is. This means that if you are a group of 1 person only, you have to address only the first functionality. Otherwise, if you are a group of 2 people, you have to do the first one and the second one, and so on and so forth. So you have seen that the amount of work that is requested is proportional to the number of students. I think this is a fair decision. If you are a group of 4 people, please send me an email because I have to give you the MyRio board. Basically, I will lend you the board when you come to my office, and then you will have to return this with the assignment, with the delivery of the assignment. This means that you can keep the board for you, okay? So if you need to do also the national instrument part, because you have a group, you are in a group of 4 people, you can take the stuff with you, you can keep it as long as it is needed to deliver the assignment. The deadline is end of July. This means that you have time to work starting from now to wherever you like, provided that you deliver by end of July. The delivery will be done through Portale Didattica. Please stick to the requirements, so deliver just 1 zip file where you placed all the material that is requested, and then there will be an evaluation, and the result will be posted online, okay? If you have any doubt, question, please feel free to ask, otherwise I will start with the lecture. Do you have any doubts, question on the assignment? Okay, so let's start with the lecture of today. So today I want to focus on one important aspect of the development flow of ISO 26262. This is relevant for 2 reasons. The first one is to give you a broad picture of what testing could look like. You can see here that there are many things that have to be considered, many activities that have to be developed. The second reason is that it is very likely that you, when entering a company, you will be in charge of doing testing. This is because in order to develop good tests, you need to have a good understanding of the product that you are testing. And this is typically the way through which companies train new recruits. If you want to deliver the knowledge about the product to a new engineer, let's ask the engineer to develop some form of testing for that product. This is the way through which you can study the details of the product. Then you deliver some useful work for the company while you are learning. So that's why I think testing is important for you, because sooner or later you will have to do tests. By the way, you will have to do tests for the assignment, but this is just a minor part. I'm really convinced that you will end up doing testing as first job out of Polytechnic. So that's why I decided to have this lecture. So as always, we have an outline. We will look into first an introduction to give you the broad picture. Then we'll focus on the 3 types of testing that are foreseen by the ISO standard and that are the de facto standard that is used in industries. So we will look a bit into unit testing, integration testing, and system testing. We will recap some of concepts that we already have seen together, but we will delve into some aspects that we have forgot till now. Well, first of all, let me give you the idea. If you may remember, we had the first part of the class that has been focused on ISO 26262, We did the concept phase, so we analyzed an item, we analyzed the different implications of failures in this item, and we end up as a last step of our investigation into the definition, with the definition of the functional safety concepts. So we know that something can go wrong, we know that this can impair the functionality delivered by the system. We know that this impairment can have implications on the life or the health in general of users of this system, as well as those people that may be around the system when it fails. And so we have to manage these misbehaviors. Our system, as I hope it is now clear, is made part of hardware, part of software. The hardware can go wrong due to hardware faults. Something gets broken. So we have a resistor that stops working as expected. We have a pin on our chip that is broken. We have a lastly coupled interconnection so that we lose the input from a sensor. There are many reasons why we can have a fault. But in general, these are hardware faults. These are manifestations of a physical problem that is affecting our system. Then when considering fault in software, well, we do not have something that gets broken. The software doesn't get broken. Either the software is working or not because it is affected by a bug. Okay? So we cannot see the manifestation of a fault in our software that happens because something is changed in our software. The software is either correct or not since the shipment of our item. This means that if we have countermeasures against hardware faults that are based on several techniques like the range check on input and output data. Do we have a broken sensor? We can discover this because the sensor either is never producing any input or it is producing inputs that are outside the validity check range of our input. We can have plausibility checks. So we are getting data, but those data are not consistent. Let's say we are getting two different data that are somewhat correlated, and checking the correlation between the two inputs, we see that the correlation is not what we are expecting. Well, this is an indication that something is going wrong. We can have the capability of detecting data errors, for example, through redundancy. We have a duplication of the data, we read 2 times the same data, then we compare, it is different. This means that there is an hardware fault, maybe in the memory, maybe in the address logic, maybe in the comparator, but no matter what, there is a fault. We can have control flow monitoring. Let's say we can have a device that looks into the way in which the software is executed to check whether the operations are the one expected according to the knowledge that we have of the software or not. If this is the case, it could be an indication of an hardware error. Or we can even have multiple instances of the software implemented on multiple instances of the hardware that are different, and then we can compare the outputs if the two are doing the same, if all the instances are doing the same operations, but the results are different, it means that something is broken. So this is to say that when consider the hardware faults, we have very, let's say, simple techniques that consist in adding more hardware than what is actually needed for the functionality to prevent misbehaviors due to failing components. Well, with the software, we cannot approach the problem in the same way. We have to deliver a software that is bug-free. So this cannot be done just by adding other instructions, because it is very likely that you add other bugs. What we have to do is to put at work a process that assures that the quality of the software is the highest possible. This means that we need to have countermeasures against bugs that allows us to ship a software that is bug-free. How this can be done? Well, this can be done through an educated software development process. This means that we need to have a technique that is responsible for tracing the requirements. We have seen that multiple times in the ISO 26262, we have to state first what we want to do, and then we have to do that, and then we have to check whether we did the things properly. Well, in practical terms, this means that you will have documents that contains specifications of what the software has to do. Then you will have code implementing those specifications. What you need to have is a link between the specification and the code, so that you can make some checking like, let's validate whether all the specifications has been implemented. So you see, simply speaking, whether any specification you have in your document is corresponding to at least one piece of code in your implementation. If this is not, it means that your software is not compliant with the spec. This means that some functionality is missing. Similarly, we can check whether the piece of code that we have is corresponding to a specification. If not, this means that either there is a lack in the specification or the designer made some mistake because the designer implemented some functionality that is not needed. Then we need to constrain the flexibility of programmers so that you cannot write whatever you want in your program, but you must adopt some specific subset of the programming language of choice to guarantee that you will not make software that can contain hidden functionality that you want to avoid, or that it is so complex that you cannot test. We'll talk about this later on. Or you want to adopt a model-based design approach that we have addressed already, that allows you to generate the code automatically from a certain specification that is a model. In this case, the model must be linked with the document listing the specs that you have to implement. The code, as you have learned, is generated automatically, so you can enforce some coding rules automatically, so your work will be easier. And then you need to do tests. You need to test every element of your implementation in a structured ways, so addressing the problem first on the single entity of your design, then on the all entities together of your design, and then eventually on your design deployed in the real system, so that you can be reasonably confident that no hidden misbehavior are still there. Only if you are able to put together all these ingredients, then you will be able to provide a good quality software. Well, I know that you are mechatronics students. I know that you may be puzzled why we are talking about so heavily about software. But remember that software is everywhere. In any mechatronics system, there is a computer that interacts with something else. And everything is regulated by software. So software is mandatory. Software is responsible for a safety-critical and mission-critical system. So on your road to work, there will be software. In some form or the other, you will have to deal with software. So better if you have this knowledge because they can help you in doing better your job. So what is software testing? Well, if you look into the glossary of terms of IEEE, you can see that software testing is considered the process of analyzing a software item to detect differences between what the software is doing and what the software is expected to do. So this can be expressed in this way. So we start with a requirement. This is a document describing what the software has to do, or it is a model describing what the software has to do. Then given the process that we are using for coding, either manually or through automatic code generation, from the requirement we derive an implementation. So to put this in the concept of what we have done in the past weeks, let's imagine that the requirement is the Simulink model that describe the functionality that you want to implement. Then this arrow here is embedded coder that produces an implementation that is a piece of C code. Okay? Then the test requires that starting from the requirements, so starting from the knowledge of what your software shall do, you derive test vectors. These are input stimuli that you want to apply to your implementation to produce relevant outputs. Along with the test vectors, so the input stimuli that you want to feed into the system, you will also have the expected outputs. So you know what the system has to do. You have written the specification, or you have read the specification very carefully so that you have a very clear requirement of what the software has to do. So you know which is the relationship between input and output. So based on this knowledge, you create the input stimuli, and for each input stimuli, you produce the expected output. Then you have to feed the test vectors to the implementation of your requirement. And you have to record the produced output. Well, you can do this at different levels. You can do this when you develop the model that you animate with input stimuli, then you simulate the model, you check the results, whether they are compliant with what you are expecting or not. Or you can do this running the software. So you feed the software with inputs, you record the outputs. Then you have to check whether what you got out of your implementation, given the test vectors, is the same or is consistent with the expected output. Well, if your implementation provides the expected outputs, then the software is correct. And so you can move to the next functionality to test. Otherwise, there is some difference. And so you have to investigate why there is this difference. Basically, you have to look for the bug. Here you can see 100% coverage. Well, what's the meaning of this? When you test, you have to test enough. This means that you cannot just provide the first input that comes to your mind, check whether the output is the expected, and that's it. You have to feed your implementation with a sufficiently large set of input stimuli so that all the possible functionalities that are contained in your implementation are tested. Well, we will have metrics, we will see them in a minute, to understand how much to test. So we will have some structured techniques for both generating the input stimuli and to measure whether we tested enough or not. This reasoning seems to be very vague, but besides the technical aspects, there is a huge cost aspect that have to be considered. This is more or less a chart that you may have seen in other classes, but gives you a rough idea of how the cost of finding bugs scales with the moment in the lifetime of an item where you discover the bug. So these are absolute units. What is relevant is the proportion that you can see here. Let's imagine that you find a bug at the requirement phase. This is because you did your modeling with Simulink, you did the simulations. Then during the simulation, you discovered that you made a wrong estimation on gain in your model, or you implemented a portion of the state flow that is not completely consistent with the requirement. Well, in this case, you are still at the requirement phase, so the cost is 1. Then if you start with your design, you define the architecture of your system, you start dealing with the different elements of the architecture, and you find a bug there, the cost is 5. So you can see that with a single step, we already had a huge increase in the cost. This is because the more you move towards the delivery, the more are the details that you have on your item. And so the more is the effort that you have to put in order to add these details, analyze these details, investigate on possible discrepancies between what you have and what you are expecting to have. Then if you code, and then you have to fight for a bug in the code, well, the cost is 10. So this is the number of hours that you have to spend in order to understand why, under certain circumstances, you don't get the output that you expect, but something slightly different. Or why the software crashes with a division by 0 that is not expected to happen. When you integrate your code on the hardware platform that is used in the system, and this item is integrated with the rest of the application that are possibly other ECUs, mechanical parts, and so on and so forth, the cost of finding a bug becomes 20, because the details that you have in your system are much more. So it is very difficult to understand where the problem comes from. Is it a problem due to an operation that is done at the wrong speed? Is this due to a strange mix of functionalities that happens when, for example, one event is happening and another event is happening, and the combination of the two is not trivial? I'll give you an example. It is taken from railways, not from automotive. There is a company that is building trains that had a huge problem. There are problems on the pantograph, that is the element that is on the ceiling of the train that connects with the electrical wiring. And there was a problem that seems unrelated on the automatic opening and closing of the doors. These are two totally different problems at the first sight. But then there was an investigation that requested analyzing huge amount of data with, it means terabyte and terabyte of data, with advanced techniques like data mining, in order to discover that when the train is a high-speed train, moves from the high-speed electrical segment of the railways to enter in a station, the pantograph is subject to a huge voltage drop. Could be from 25,000 volts to 5,000 volts. This is creating a shock on the pantograph, and that's why the pantograph breaks. But then the design was done in such a way that the electrical circuit of the pantograph was, let me say, the same as the electrical circuit that regulates the opening and the closing of the doors. So the problem of the voltage drop when entering and exiting the railways that created the shock on the pantograph was also creating a shock on the door. Okay? Well, this is not trivial at all. In order to understand that, at the testing phase, you have to take the train and having it moving on the high-speed line for many hours in order to generate a number of shocks high enough to show the problem. So can you imagine the cost of doing this? It's very huge. If you are able to analyze better the design and find this problem just by looking at the electrical circuit and having the, let's say, the width of understanding this voltage drop problem, maybe you can discover this at the design phase. So you can save one order of magnitude in cost, okay? Then if you deliver this to your customer, the cost is becoming very, very huge. Think about Alstom that is making the ETR 1000, so the new high-speed train. Well, the problem that I was mentioning is on that train. So if you discover that, you have to stop the train, you have to bring it home to make the restoration. And while the train is under maintenance, it cannot travel, so you lose money. And guess who is charged by Trenitalia for this problem? The company that designed and manufactured the train. So the cost is huge. This is because it is not just a matter of cost that you have to spend for having your engineers that are solving the problem. It may be the case that you have to pay the customer that both your item that cannot use it because there is a fault that you overlooked. Okay, that's why testing is important. You must address test in a structural way. Sometimes tests can be considered boring by engineers because the usual attitude is, come on, I am an engineer, I want to design. Well, testing is very, very important. Sometimes a good engineer is mandatory to do a good test. So don't feel, let me say, underrated if you have to be involved in testing activity at the beginning of your career. Then, after this, let's have a look at the different flavors of test. It's important to understand that there is not just one single type of test. There are multiple types of test. You can have functional testing. This is intended for checking whether all the functionalities that has been specified has been implemented properly. Then there can be a performance and robustness test. This means that you want to verify whether all possible working conditions, the functionalities are behaving as expected in terms of time, in terms of capability of handling the worst case scenario that could happen in your system. And then in some cases, you can also have the security test. So you want to be sure that only those that are allowed to perform certain operations are able to do that operation and your system is able to enforce protection mechanism. Well, this is clear if you think, for example, to big software system for managing the operations of banks. You don't want to have somebody that is not intended to do that enters in your bank account and steal your money. This is also becoming very important in other applications like automotive. Today we have more and more connectivity inside automotives, so we want to be sure that nobody can enter in our vehicle doing some unpleasant operations that can harm our life or can, let's say, bring us to some unpleasant situations. Well, if we stay on the functional testing, we can see that we have different flavors of functional testing. We have the unit testing, where we consider the single elements of our design, that is the single atomic fragment of code that we assign to our designer, that is the unit. And we just look into that unit without considering the other units that are making the entire system when grouped together. So we do unit testing addressing the single functionality. Then, after we integrated all the different units, well, we have to check whether they stay together nicely. And so we have to do the integration testing. So when all the components are grouped together, we have to check whether the assembly is still behaving as expected or not. Then we have to deploy our item into the final application, that is the system that is using our software. And again, we have to check whether the assembly of functions deployed in the real system behaves as expected due to the interaction with the real elements that are in the system. So this is reflecting the V-cycle. This is not the first time we saw this chart. We have already commented this when dealing with ISO 26262, when dealing with model-based design. It's always the same story. We have a system that we must design. This system is made of different elements that are our items that are connected according to a certain architecture. Then the different elements of this architecture shall be designed and implemented. Then when testing the results of our implementation, we will address first the single elements, then we will address the integration of the elements, and then we address the deployment of the elements in the final system. So, given this overall picture, we will delve into the different phases of testing because this will give you some techniques that I think are important. Looking into the unit testing, our goal is to confirm that each unit of the design works properly. This means that we have to address all the units. There can be one tester, that is in charge of addressing all of them. We can have multiple testers that works in parallel because the functionalities of our system are so huge that a single person cannot do the job in a reasonable time. This is normally the case of automotive applications where you have hundreds of specifications for hundreds of functionalities that are implemented by tens of units. So you may have multiple persons that are working on the same product at the same time. Here, it is a testing phase. So we need to understand what the unit has to do. We need to generate a sound set of inputs. We need to be able to understand which are the outputs expected given those inputs. And then we have to apply those inputs to the unit, and we have to check whether the outputs are the expected one. How can we do that? Well, the standard suggests us some methodologies. We can do requirement-based test, we can do interface test, fault injection test, resource usage test, back-to-back comparison between model and code if applicable. So we have a number of methodologies that are suggested. For what concerns the unit testing, well, for sure we have to do requirement-based test. This means that we need to be able to analyze the requirements that somebody specified for the unit, and then based on this analysis, we have to generate the test properly. This is done using techniques that are presented here, that are the generation and analysis of equivalent classes, the analysis of boundary values, and possibly also the error guessing. This is the way that allows us the capability of deriving tests. We will look into these techniques in a minute. For the moment, let me just say that this is just half of the coin. So how to generate tests. The second half is how much tests we want to generate. So we have an instrument that allows us to generate tests, but then do we have to generate one test, two tests, 100 tests? How much we have to generate? Well, this is given by metrics. The metrics have to be applied on our software to get measures that tell us whether we tested enough or not. And these measurements are statement coverage, branch coverage, and MCDC. We will address them in the next of this presentation. So let's look into the techniques to generate the test. We said a minute ago that those techniques are based on equivalence, class partitioning, and boundary value analysis. What is this? Well, if you think to the functionalities of a system, well, normally the specification says the system has to deal with inputs that could accept values ranging from this to that. Based on the different inputs, you have this functionality to be done if the input is in this boundary, that other functionality if the output is done in that boundaries, and so on and so forth. As an example, let's imagine that we have a functionality for a system with these requirements. If x, the input that is provided, is between 1 and 50, then we have to perform the action 1. If x is between 51 and 100, we perform action 2. If it is less than 1, we perform action 3. If it is greater than 100, we perform action 4. Okay? So you can see we have 4 requirements that links the subset of the possible input values with a specific action. Well, the equivalence class partitioning tells us that the input domain can be divided in disjoint subdomains. Those subdomains are grouping inputs to which the same action is associated with. For example, if we consider these requirements and these 4 actions, we can see that the space of all the integers, that is the data type of the input x, can be partitioned in this way. So for all the elements that are greater than 100, we have this area here. For all the elements that are smaller than 1, we have this other area here. For all the elements that are between 51 and 100, we have this subspace. For all the elements that are from 1 to 50, we have this other subspace. Okay? So when you want to test the 4 requirements and the associated 4 actions, you don't have to apply to your system all the possible value of x. You just have to pick up one instance from each equivalent classes. So if we take, for example, 110, we feed 110 into our software and we activate the action 4. If we take 200, 400, 500, we always activate the same action 4. So there is no point in applying all these values to test A4. We just have to take one input out of this subspace. And the same for the others. If we want to test what the system is doing when x is below 1, well, we can take 0, or we can take 2, or we can take minus 50. There is no point in taking all of them, okay? Because all of them will just activate always the same function, okay? So this is very important because if you think about the set of possible inputs that you can apply, this can be very huge. Think about the integers. Let's imagine that those are represented over 32 bits, as in all 32-bit microprocessors. This means that if you don't use the equivalent class partitioning, and you want to test exhaustively your functionality, you will have to apply 2 to the power of 32 possible inputs to your function. So if your test takes just 1 second, well, you will have 2 to the power of 32 seconds to do the testing. That is 4 billion seconds. I don't know how many years it is, but it is a huge amount of time. Well, it is pointless to do that. If you can analyze your requirements and you can do the equivalent class partitioning, roughly speaking, you can test your functionality, obtain the same result that you got with 4 billion inputs, just using 1, 2, 3, 4 inputs, okay? so you save a lot of time. Remember that testing can be very expensive because you have to derive inputs, you have to apply inputs, you have to check the outputs, and then you have to do this systematically so that you tested enough. We will see in a minute what does it mean. So exhaustive testing, that could be the brute force approach, doesn't apply, simply because it will take too much time. You need to find a clever way for identifying your tests, okay? Then, partitioning can be done in different ways. Normally, your system has multiple inputs. Your unit has multiple inputs, not just one. So you can treat all the inputs independently, and so you can make the partitioning of the input space considering first the first input, then the second input, and then the third input, and so on and so forth. And then you pick up one test, getting one element out of each of the different partition classes that you got for each input. Or you can do multidimensional partitioning. This means that you consider all the possible combination of the multiple inputs of your system. Let me explain this with an example. Let's imagine that we have a function that is accepting two inputs, x and y. Again, they are integers, okay? Then we have different functionalities to be applied. If x is between 3 and 7, something happens. If it is below 3, something else happens. If it is greater than 7, again, something else happens. And the same applies for y. So if you do unidimensional partitioning, you consider x and y independently. So you will pick up 6 tests. You have x smaller than 3, y don't care. X, you have to take one element in the range 3 to 7, y is a don't care, and then you have to take one element for x greater than 7, y is don't care. And then you do the same, considering x a don't care, and reasoning on y, okay? So you will have 6 tests, and they are built considering the inputs as independent elements. If you do multidimensional partitioning, well, you consider the Cartesian product of x and y. So if we draw x on this axis and y on that axis, you can see that you can represent the different classes in this way. You have x below 3, in between 3 and 7, and then greater than 7. For y, you have below 5, between 5 and 9, and then above 9. If you draw axes, you partition this Cartesian space in this way. Then the test is built by picking up one item, one point, in these subspaces. So at the end, you will have 9 tests, okay? This is because you consider the possible interaction between x and y, okay? So what is the best solution? Well, there is not a definitive answer to this question. Sometimes it is a matter of how big is the set of inputs that you have to consider. If you have a function with 10 inputs, well, doing the Cartesian product is quite complex because you have to combine multiple scenarios in a non-trivial way. So maybe it is better to adopt a unidimensional partitioning. If you have few inputs, well, you can consider the multidimensional partitioning as we did here. Then, this is one technique. You consider the requirement, you analyze how the inputs can be partitioned, you pick up items, one element for each equivalent classes. In this way, you have good tests. Then, some improvement can be done by considering that the programmers more or less always do the same mistakes. As an example, let's imagine that you have to implement a piece of code like this one. if x is greater or equal to 0, do f1, otherwise do f2. Well, if you analyze what programmers are doing, often happens that you end up writing this code. You omit the equal. This means that you have to check for below than or equal 0, and you just check for smaller than 0. Think about your first program that you wrote that, that does operation with arrays. An array of 10 integers. You do a loop on this array. You do the loop from 0 to 9, okay? Typically, the first mistake is to do the loop from 0 to 10. All of you did this mistake the first time that you wrote a piece of C code doing operation with arrays, okay? This is very typical. And the pattern is the same. So if you analyze the mistakes that programmers does, due to, let's say, many reasons. That could be inexperience, it could be the need, the pressure, so the need for delivering your code soon, the fact that when you wrote that line of code you are tired because it is 8 hours in a row that you program, and so on and so forth. Well, you make these mistakes. So the test community recognized this and developed these techniques that is quite stupid, but very effective. That is, well, based on the concept that when you generate tests, it is better if you produce tests that consider inputs very close to the boundaries of the equivalent classes. Let's say, let's imagine that we have this partitioning. So you can pick up one value in these classes, and that's okay. But it is better if you take values close to the boundaries and on the boundaries. This is because it is very likely that a good amount of bugs are associated with the conditions that are related to those boundaries. Let me give you an example. Let's imagine that you have a certain function that works with x, and then if x is between 99 and 999, you do something, otherwise you do something else. Well, if you want to do the equivalent classes partitioning, you will find that you have 3 classes. Below 99, between 99 and 999, and above 999, okay? So if you want to generate tests, good tests, look for the boundaries, and then pick up tests within the classes, close to the boundaries, and on the boundaries. This means that a good test for this function would be 98, 99, 100, 998, 999, and 1000. So in this way, you pick a value exactly on the boundaries, and then a value in one equivalent class close to the boundary, and then others in the other equivalent classes close to the boundaries, okay? Well, you have to do this systematically. Whether you are testing a stupid function like this one, whether you are testing your new ABS function or whatever. So you have to look into the specification, you have to understand what are the ranges for the inputs, and then you have to derive tests based on this knowledge. Well, example, you have a distance sensor that is expected to produce inputs in the range from 2 centimeters to 4 meters. Whatever is above 4 meters or whatever is below 2 centimeters, it is wrong. So if you do your assignment, as you will have to do, that is making use of that sensor, it would be wise to test the functionality by providing inputs according to this specification. So you will partition the input space accordingly, and then you will pick up inputs accordingly, okay? This is just to give you a very first and direct usage of these concepts. Well, this is the techniques that is used everywhere for doing testing. If you go to Theorese, if you go to Altran, if you go to Accenture, if you go to whichever other consultancy company, Reply, whatever, and you are put at work doing testing, this is what you have to do. Then, how much to test? So we have to derive tests. We know how to do that, but how much tests we have to derive? Well, we can do guessing, but this is not always the right approach. Better if we have some metrics that measure the quality of the test. Well, those metrics are available. They are on the software engineering scenario since decades. Well, ISO 26262 decided to adopt some of them. Those metrics are statement coverage, to measure the percentage of the statements of your unit that has been tested. The branch coverage measures the percentage of the branches in your unit that has been tested. And the modified condition decision coverage, MCDC, that measures the percentage of the conditions that affected independently the outcome of your unit that has been tested. Well, we will see an example of this. So let's imagine that we have a very simple function that takes two inputs, integer inputs, x and y, and this is the specification of the function. So int z equal to 0, if x is greater than 0 and y is greater than 0, we do this, otherwise we do that, and then we return the value, okay? So this function is made of 4 statements. If, so the statement 3, the statement 5, the statement 7, and the statement 9. So statements are lines of code that executes modification on inputs to produce outputs. Int z equal to 0, this is a variable definition, okay? This is independently executed every time you call the function for. So you don't have to generate a test for that line of code. It is always executed. So we don't count it. Then we have one if. The if produces 2 branches. The branch corresponding to this value evaluated as true. So when x is greater than 0 and y is greater than 0, we do line 5. And we have the other branch that is the branch 7. Okay? So one if statement, 2 branches. And then we have 3 conditions. So the conditions are the combination of inputs that can produce both the value 0 and 1 for the Boolean expression that is in our branch. So if both these two, so x and y are greater than 0, so this first comparison is true, and this is true, then we do z equal to x, the first condition. If this is false and this is true, we go in the second one. If this is true and this is false, we go in this one. If both are false, well, this is a condition that is already considered in these 2 other conditions, so we don't have to take care of that. So that's why we have 3 conditions. Okay, these are the possible statement branches, a condition we have in our code. Okay, so if we want to have 100% statement coverage, we must find a test for testing the 4 statements. If we want to have 100% branch coverage, we have to find tests to execute both branches. If we want to have 100% MCDC coverage, we must find a test to satisfy all the 3 conditions. Okay? Then, if we analyze the equivalent classes and we do multidimensional partitioning, we have this picture. So we have the space where x and y are greater than 0, the space where x and y are both smaller than 0, and the other 2 subspaces. Okay? So, which are the tests that we want to generate? The first test is, let's say, 1 and 1. We do not do equivalent, we don't do boundary values analysis here. We just take 1 point in this subspace. So for x and y, both greater than 0. If we apply 1 and 1 to function foo, this means we call this function with x equal to 1 and y equal to 1, well, we execute this statement, then we execute that statement, and then we execute this other statement. So we execute 3 statements out of 4 possible statements. Okay? It seems trivial. Is this clear? So that's why we have 75% of statement coverage. We executed 3 statements out of 4 possible statements. For the branch coverage, well, we have just 50%. This is because we only execute this branch. We do not execute this one. And for the MCDC, we tested 1 condition out of the 3 possible. So this is not enough. The quality of our test is too low. We want to have 100% on all these coverages. So we need to do something else. Let's generate another test. Let's say 0, 1. If you execute this function feeding with x equal to 0 and y equal to 1, you will see that you cover all the statements, you cover all the branches, but not all the conditions. So you need another test. And eventually you come to 100%. So what could be the work when doing testing? First, you take your code and the specification. You analyze the specification, you derive the equivalent classes, you do possibly the boundary values analysis, and then you start writing the first test. You run your software with the input corresponding to the test, and then you measure the outcome of your function. First, you check whether your function is doing what you are expecting. So you check whether Z is exactly what you are expecting given the test. So if you provide test 1, 1, the expected output for Z is 1. So you check that. Then you measure how many statements, branches, and conditions you executed with that test. Is the output the one you're expecting? Good. So no bugs found. Are all the coverage to 100%? Good. You are done. Move to the next unit. If this is not, well, if the output is not the one that you are expecting, there is a bug. You send a bug report to the developer. You have to fix this bug. Otherwise, if the output is the expected one, you check the coverage. Are the coverage 100%? No. Then new tests have to be generated. Okay? This is the work. Then, what about interface test? The interface test shall be done in order to verify whether the unit sends out data in the appropriate format. So, and then to check whether the unit receives data in the appropriate format, and then whether the behavior of your unit is known if the inputs are formatted correctly. Example, your unit shall perform a certain operation like this one. So if you do the interface test, so you derive tests as we have seen so far, and then you check the output of your function, well, you will see that there is a certain condition that is the one that you can see with test 2 and test 3 that brings the function to return an unknown value. This is because the initialization here on line 2 is not done. You just declare the function, the value, the variable z, but then if x and y, one of the two is greater than 0 or equal to 0, you never assign a given value to z. So the function returns an unknown value. Okay? So with the interface test, you are checking whether the outputs provided by the function are consistent with the input and whether they are formatted correctly. So in this case, it is clear that with this test, you can find this bug because there are at least 2 test cases where the output of the function is not defined. Okay? This is again another typical error that you do when starting programming. Then, fault injection, we just look for the concept, we don't go into detail of the techniques. The idea is the following. In our item, we employ some functional safety concept. This means that some of the functionalities that our item is showing is intended to operate only when there is a failure. So we have a fault affecting our system. This fault can become a failure, so it can inhibit the functionality of the system. Well, we have some countermeasures against this. So how can we test them? Well, we have to artificially inoculate a fault in the item to check whether the functionalities that we added for fault management are working or not. This is the purpose of fault injection. Artificially inoculate misbehaviors to check whether the item is responding correctly or not. So as an example, let's imagine that we have a very simple function that makes a sum. We inoculate the fault in our item, and then we check whether the response of the item is either consistent with the expected output or not. What could be the outcome? Well, you can have a correct output no matter if there is a fault in the system. This is because you designed your system to be robust against fault, so that the system always provides this correct output, even if there is a broken component. Or you can have an item that says, there is a failure, don't trust on my output. Okay? So you just have a technique to detect the presence of the fault. No matter which is the options that you decided to adopt, you need to test it. You need to test whether your item is producing the expected behavior or not. And there are techniques to inoculate artificially faults and make this kind of test. So here on the slides that are already on Portale Didattica, you can find the different, a description of the different elements of a fault injection system. That is the system that allows you to inoculate those faults. We don't go into them. We just skip these slides, and we go into the resource usage test. The resource usage test is the test that you have to do in order to check whether your unit has requirements in terms of computing capabilities that are consistent with the execution platform that you will use. Let's say that you take your software, you cross-compile it, and then you check how much memory it is using, how much flash memory it is using, which is the execution time of the software, to check whether those requirements are consistent with what the platform sets available to you. We have seen that in our application, we may have to use microcontrollers with limited memory capability. So if our algorithm is using megabytes, but our microcontroller only offers kilobytes of memory, we have problem. We fail the resource test usage. Then we have seen that we have to schedule our task according to a certain frequency. Let's say we have just 100 milliseconds to execute our unit. But our unit is doing so much complex operations that it takes 150 milliseconds to execute. Again, we failed the resource usage test. The execution time is not consistent with the budget that is allowed. Okay, so these are tests that we have to do before committing our unit to the integration phase. How can we do that? Well, as far as memory occupation is concerned, we just have to build our code and look for the building and the linking reports to measure the amount of memory that is used. For the execution time, well, we have to run our unit and measure the time it takes while running with the test cases that we defined. If the time is consistent with the budget that we are fine. Otherwise, we have a problem. Finally, is the back-to-back comparison between model and code, if applicable. Well, this is something that we want to do when exploiting the model-based software design. So basically, what we have is an executable model of the behavior that we have to expose given a certain specification. This could be, for example, a Simulink chart with some signaling blocks plus state flow and so on and so forth. So this is an implementation of the specification. So the first operation we want to do is to iterate through this loop, doing model in the loop simulation to check whether the model is consistent with the requirement. When we are happy with this, we generate the code, and then we have to do operations to validate whether the code is behaving exactly as the model. And this could require software in the loop, processor in the loop, and hardware in the loop simulation. We already have seen this, but let me recap the concept. So in our flow, we have always a controller and a plant. The controller is fed with a reference. Then the controller compares the reference with the status of the plant. If there is a discrepancy, the controller applies a modification, a command to the plant. So this is a closed loop control. In model in the loop, we have modeled with the same language. It could be Simulink, it could be Modelica, it could be something else like MATLAB, the controller and the plant. And both are simulated using a computer. So this is where you refine the model of the controller and possibly the model of the plant until the plant is modeling with a good level of fidelity the physical system that we have to control, and the controller implements the specification properly. So here you can simulate as much as you want. Then we translate the controller into software through embedded coder. And then here we have no more a model, we have the C code resulting from code generation. Well, when doing software in the loop validation, on the PC we execute the controller software and the model of the plant to check whether the two are behaving as expected. Or, let me say, we check whether the controller is still behaving as we modeled. Then, with processor in the loop, we take the controller and we brought this to the embedded hardware. So here we are running the controller on the processor that is the processor of the final application. And again, we stimulate this with a model of the plant to check whether the response is the expected one. Here, we are still looking into the functional property of our controller. We don't look into the performance aspect of the controller. This is because being the plant simulated with a computer, we cannot have a real-time behavior. So it is not possible to have the plant that reacts with the same time that we will have in the real physical system. So this is just intended to see whether your controller translated into software works nicely on the embedded processor that you will have in your application. Finally, we have the hardware in the loop. With the hardware in the loop, we have the controller software deployed on the embedded system, while the plant is modeled still in Simulink, but it is no longer executed by the PC. It is executed by a dedicated hardware, like the one that I'm showing you here, that is intended to run the plant with the same timing of the physical system. So this means that if your plant has to react in 10 milliseconds due to stimuli coming from the controller, the hardware here will respond exactly in 10 milliseconds, as the real system will do. Here, it is not the case. It could be the case that the simulated functionality reacts in 1 second. This is because the model has to be solved on your computer that is not suitable to represent with a good level of fidelity the timing properties of your system, of your plant. Well, obviously, it would be nice if we can always work at this level. We have a very accurate representation of the plant. Well, the problem is the cost, as always. So if we do simulation with Simulink, we can have to spend a couple of €1,000 for the PC, plus, let's say, €10,000 for Simulink. With 12K, more or less, we are happy. Here, we may have to spend €50,000 for one of these boxes, plus €10,000 for the software to manage this box, so it is already 60K, plus the €10,000 of the Simulink license, plus the €2,000 for the PC. So you have a 60K difference from this slide and this one. So if you want to work in the embedded system business and you have to deal with a mechatronic system, well, you have to put this at work. So you will have to spend the money for this and you will have to spend the money for that. Obviously, if you have 10 developers, it is very likely that you have 9 of them working with this approach and only 1 working with this, because this is too much expensive. So most of the activity will be done in the model in the loop and the software and processor in the loop approaches, and only the final checks will be done here. So this also fits nicely with the flow that we have seen so far. We spend most of the time talking with about functional test and interface test. These are all operations that you can do with model in the loop, software in the loop, and processor in the loop. Only when you have to do resource usage testing, you have to move to hardware in the loop. So it is reasonable to have most of the tests are working with model in the loop, software in the loop, and processor in the loop, and only one tester working on the hardware in the loop phase. Then the back-to-back comparison test is this one. So you have test cases, you have the model in the loop, you have the software on processor in the loop, and you check the outputs of the two. Are they the same? We are happy. They are not, we have a problem. Okay? Is this clear? Okay. Then integration testing. Well, integration testing is where you move up in the ascending branch of the V cycle. That is, you put together all the units that you already tested, and you check whether they are working correctly or not. So here, the focus is no longer in testing the units. It has already been done. Here, you have to check whether the different units works correctly together. And again, we have a number of possible methods suggested by the test. Nothing very special here. The only difference is that the metrics that we are using are different. The techniques to generate the test are the same of unit testing. So we analyze the requirements, we perform the equivalence class partitioning, we do boundary values analysis, and that's it. But what drives our testing is different. We are no longer interested in the statement of our code. Here we are looking at how the different units are executed. So we will be looking into the function coverage. So are we calling all the functions executing all the functions of our code at least once? So let's imagine that you have a code that is made of 10 functions. This is because one unit has 5 functions, another unit has 3 functions, and another unit has 2 functions. So integrating together all the units, we have 10 functions. In the integrated program, do we call all the functions at least once? If yes, well, that's a good indication that all the functions has been properly linked together. No, this is not 100% function coverage. Well, there is a problem. Some part of our code is not integrated correctly because there is a function that is never called. Either we made some mistake in integrating together all the functionalities, or we designed a function that is useless, so we can remove it. The call coverage looks for all the places where a function is called. So this is because in your code you may have the need for calling the same function 10 times in 10 different places. So if you look to the function coverage, you are happy when your function has been called at least once. But when you look at the call coverage, you are happy only if you executed all the 10 calls to that function. Okay? So you have to measure how many times a function is called and how many times the call to that function are executed. Are all the functions executed? The function coverage is 100%. Are all the calls to all the functions in the system executed? Then the call coverage is 100%. Okay? Is this clear? I'm going quickly here because I think these are quite trivial concepts. There's no point in spending too much time on that. Finally, system integration. The system integration is where we put our system, our item in the mechatronic system that is using it, and we check whether it is working properly or not in a representative environment. So the difference here is that when we do this test, we no longer have everything on our desk. We need to move in the lab. We need to move in a setup that is closer to the final application. Let me give you examples. Here is where we do the hardware in the loop testing of, for example, an entire vehicle simulated with this rack from this space, 200,000 euros. Plus, here we have all the different ECUs that are in our final vehicle. So one of these ECU is the one that we want to test. So all the rest of the system will work in such a way that we are able to test whether the functionalities of our ECU are produced as expected when it interacts not with a very, let me say, abstract model of the real system of the plant, but with the real plant modeled with real-time properties. Another possible scenario is this one, where we have our ECU that is interconnected through the vehicle network with all the other ECUs that are to be deployed in the vehicle. As an example, this is what you can have. This is Opel virtual prototype of a vehicle. So here you have all the cablings of the electrical architecture of the vehicle. So the very same cables that you have in the real car, you will have here. You will have here all the ECUs, all the sensors that can be placed here, plus an hardware-in-the-loop system to model everything that is not electrical, that cannot be attached to this device in a simple fashion. And here you have really the driver's seat, the steering wheel, you have the accelerator pedal, the brake pedal, you have the clutch pedal, you have the gear lever. So basically you have a very detailed model of your vehicle, and here you are interacting with the vehicle with this model as the real driver will do, and all the electrical elements of the real vehicle cooperates as it will happen on the real vehicle. This is the, let's say, last mile. That is, when you come to this point, you already did a lot of development and testing activities. Here you are putting together everything to check corner cases that could be harmful if the test is done on the real vehicle. So you want to bring to this system to the extreme conditions to check whether everything is working correctly. Finally, you move to the test vehicle. The test vehicle, you have a real vehicle with the real engine, the real chassis, the real suspension, so on and so forth, where you integrate your software with your hardware, and you have somebody driving on the racetrack. Okay, this is the last, let's say, really the last phase that you have to do. Here is where you do field test, is where you are in the real driving scenario. First you are on a racetrack, then when you have enough confidence on the system, you go on the city. These days you can find some fancy patched cars moving. You can recognize SUV. Well, if you have seen that, it is the Levante, the new SUV from FCA that is doing field testing. Typically here you have very close to the steering wheel a very nice and red button that is the kill switch. When the driver finds that something is going wrong, kill switch, so you turn off the car. This is where the last final tuning are done. When you come to this point, you must already have done adequately testing at this level, at this level, at this level, so that you have a good confidence that nobody will get hurt when putting the vehicle on the road. Well, this is not trivial. Maybe you have heard about the new vehicle from Alfa Romeo, the Giulia. You have heard about that? Okay. 1 year ago, two Giulia were doing field testing on a racetrack that is close to Milan, Balocco. Well, suddenly there was a huge crash. One of the drivers was killed. The other one just recovered from the coma a few weeks ago. Well, they started investigating what happened. Well, there was a bug that is under investigation on the body computer that wasn't discovered properly before going to field test, so that in certain conditions, when you press the brake pedal, the brake lights are not turned on. So they were running at the racetrack at very high speed, they were very close. The driver in the front car hit the brake pedal, the red light on the back of the car wasn't turned on, the driver on the back car wasn't able to recognize the situation, they crashed at high speed. The result is that one person died, the other one was severely injured. Okay, so this is to say that what we were talking today is something that has huge implication on the life of the user. Think about the first lecture when we spoke about the unintended acceleration case. 89 persons were killed due to software bugs. So testing when dealing with automotive is not just for fun, is not just a boring activity. It is something that can save the life of people. So don't underestimate these techniques. These are things that are very important. You must put adequate care in the test that you are doing. Okay, it's 9:58. I think I spoke enough for today, so we quit the lecture. On Friday, we will have a seminar from MathTalks showing us from an industrial perspective what we have seen today together. So please come to the lecture because it is important. Thank you.